So the unit 1.2 notes 3 has to go back over and review the photoelectron spectroscopy, or PES, stuff that you guys covered when you went over the POGL. But there are a couple of things that we need to kind of talk about in terms of why Bohr's model doesn't necessarily work, and I have some evidence to support that, and why PES is a better, significantly better way to go through identifying where electrons are around the nucleus of the atom. So the first thing is that the Rydberg equation that we talked about in the last set of notes really only works for hydrogen. It doesn't work for other elements. It might work for like hydrogen and helium and lithium, and it might work for their ions, but that's about it. So that's kind of a problem. And then if the Bohr model were true, all the electrons in a certain energy level would be equivalent to each other, and we have evidence from the PES data from both the POGL and the stuff that we talked about in class to support that that is not true. And also, if the Bohr model were true, the electrons should behave like particles and not exhibit wave-like behaviors, and yet we know that they go both directions. Another way to think about it is that the Bohr model really applied classical physics. So things like motion and models you could hold in your hand, and it didn't think about it in terms of the mathematical properties of the data. But it also followed the idea of centripetal force. Which I'm sure you talked about in your physics class last year, or you just have an understanding it's the force that kind of keeps things orbiting, that you feel as you go around a corner. But Bohr's model neglects the idea of the electron being found in a three-dimensional region or sphere. So that's where it really becomes kind of a problem. Bohr's model really becomes kind of a problem. Another thing about Bohr's model is really two-dimensional, and that's also a problem because we know that atoms are not two-dimensional. So let's look at some actual photoelectron spectroscopy data. And here's hydrogen. Here's why this works. So if I were to draw the Bohr model for hydrogen, we would have the one proton, and then we would have the one electron. And that supports, so in this energy level, there's one electron. And so in the PES data, there is also evidence for one electron. So the one peak represents the ejection of one electron. So again, the way electron spectroscopy data works is that we take a large amount of energy to remove an electron. So we use X-rays, which have an incredible amount of energy, and what they do is they excite the electrons and eject them from the atom. But this particular model for hydrogen has the one electron matching up with Bohr's model, and that's why that works. Here's actual PS data for helium atom, and if we look at it like in terms of helium, there are two protons in helium's nuclei, and in helium's first energy level, there are two electrons. So if there are two electrons in the first energy level, the PES data actually supports that with the two peaks, with the one peak. So then we look at lithium a little bit, and with lithium there are three protons in the nucleus, and there are two energy levels. So in the first energy level there are the two electrons, and in the second energy level there's 1 electron. So again, this works for lithium pretty well because we see the 2 electrons in that first energy level here, and we see the 1 electron in the outermost energy level here. Okay, so that's in this particular case, based on this PES data, that supports that. Where carbon falls short is that if you draw a traditional Bohr model, with Bohr models there are 6 protons, so that means that in the first energy level we would have the 2, just like we've done in the past, and then in the second energy level we would have the remaining electrons, 1, 2, 3, 4, so that gives us our 6. But the way Bohr's model draws it shows us the second energy level has 4 electrons in it, and in the PES data there are 2 different peaks. If the Bohr's model and the PES data matched up, there would only be 1 peak. And so that's why we are using the PES data, because it is significantly more accurate than Bohr's model. Which also brings us to the idea that Bohr's model says that the atoms should only behave like particles and not like waves, and yet we do have evidence to support that electrons both behave like waves and particles at the same time. So if we look at the X-ray diffraction over here, this is for aluminum foil, and this would be indicative of particles, of electrons, very clean, distinct rings around the aluminum atom, and here would be the waves, the wave-like behavior of the electrons. And if you can see that, especially in this general area right here, there is a lot of what appears to be excess energy, whereas in the X-ray diffraction there appears to be emptier space. So this part right here is basically showing us that the electrons are really flying around there really, really fast, and they're flying around there in such a way that they are blurring the lines, for lack of a better term, and you get this sphere shape instead of a flat shape like the Bohr model suggests. So that brings us to de Broglie. And de Broglie was the physicist who was responsible for saying that electrons can behave like a particle and they can behave like a wave at literally the same time. And because electrons can do it, he got his ideas from observing light. So light worked as light waves, and as we've previously discussed and done some math with, light also can represent a photon. And so photons are packets of light. Energy. And waves are just simply what we're used to thinking about. They're the up and down, the undulating source of energy. So what de Broglie would sort of postulate, and I guess the easiest way to attempt to think about it, and I'm stringing together a lot of things here, is that each wavelength is the equivalent of a photon. So he came up with an equation, and we worked with this equation in honors chem, and if you took physics last year, you may have worked with this as well, where if we wanted to calculate the wavelength of a particle or another object, in this case electrons, we would use Planck's constant, which is the 6.626, times 10 to the negative 34 joule seconds, and we would divide it by the mass, but the mass has to be in kilograms, and we would divide it by the speed, which would be in meters per second. And so one of the things that we work with when we are doing this particular formula is a unit situation, and we ignored the units when we were in honors chemistry. Really, we did, believe it or not, and we are going to work through the units a little bit more detail this time around. But de Broglie's research brought us up to Heisenberg, and Heisenberg's uncertainty principle was very important because it basically says you can know the position of an electron, but you cannot know its speed at the same time, or you can know the speed of an electron, but you cannot know its position at the same time. So that's why I think that this picture down here is pretty funny, because if you look at the map on the wall someplace, a lot of times it'll be like, you are here, and like it points an arrow to where you're standing. But in Heisenberg's view of the world, you are probably here is a lot more accurate, because you're probably not standing in one spot for any long period of time. In terms of AP chemistry, you're not going to do a lot with the Heisenberg uncertainty principle formula. I'm just showing you this formula just because you will probably see it or it'll be referred to, but we're not going to do a lot of math with it. Basically, it's talking about change in position is equal to, or change in position times the mass times change in velocity is greater than or equal to Heisenberg's, Planck's constant divided by 4 pi. And it's a giant relationship, and I used to make the students do a lot of math with it. AP has kind of backed away from it, so I'm just making you aware of the principle, and what you really need to know about the principle is the concept or the idea, not so much the math. But if we were to work through a math problem anyway, we would want to make sure that our units are in kilograms. So I'm going to change the 1.5 milligram mosquito mass to kilograms by doing this math. I'm then going to I'm going to be solving for change of position in this particular problem, calculate the uncertainty of the position, so change of position. So I'm going to take Planck's constant divided by 4 pi, divided by the mass. And in this case, I know the speed, but we're talking about change in speed, right? So if the speed is 1.4 meters per second, right, and that's what change in velocity is, right? So if the actual speed is 1.4, but it's known within a plus or minus 0.01, what that tells me is that the change in speed at any given point in time is 1/100th of meters per second. So that's why instead of using 1.4, I used the 0.01, because it was asking me to figure out the change in position based on the change in speed. So it's a little funky, and I think there might be one problem in the textbook, or problems that maybe is in there, but for the most part, we don't worry about this concept anymore. Math-wise, we just simply are worried about de Broglie, and more specifically, about the understanding of Heisenberg's uncertainty principle at all. Now, here's how we're going to work through de Broglie problem. And I want to bring up this concept here. Keep in mind that we have to keep units in mind. So we're going to work through this together as a team, and then we're going to talk about it, and then you'll have a little bit of homework. So we know that de Broglie's wavelength problem formula is wavelength is equal to Planck's constant divided by mass times velocity. So this problem is asking me to solve for wavelength. I know Planck's constant is 6.626 times 10 to the negative 34 joule seconds. I know that the mass was given to me in this problem as 9.11 times 10 to the negative 31st kilograms. Oops. And I know that the velocity of the wave was the electron in this case was traveling at 5.31 times 10 to the 6th meters per second. So in this problem, all of my units are working out. I don't have to change anything. So I'm going to go substitute my values in. So solving for wavelength will give me 6.626. Oh boy. 626 times 10 to the negative 34 joule seconds divided by the mass, which is 9.11, times 10 to the negative 31st kilograms, times the velocity, which is 5.31, times 10 to the 6 meters per second. Now, one of the things that we ignored, like I said, in honors chem was the units. We just had you solve for stuff and basically say, just figure out the right unit, put the right unit down. But if I'm looking at this, I see that things don't cancel out very cleanly. For example, kilograms has nothing to cancel out with. joules has nothing to cancel out with. So basically, if I leave it as it is, I would have, my unit would be joules over kilograms times meters. And wavelength will be in meters, but eventually we'll convert it to nanometers. So that's a problem. And so the way that physics gets around it, and in this case honors chem gets around it, is they know that 1 joule is equal to 1 kilogram times meters squared over seconds squared. And when I talked to Geiger about this, he's like, yeah, the joule unit is a combination, is a derived unit of a bunch of other units, so it's kind of a hot mess. And I was like, oh, okay. So the way to get around that, according to physics, is to simply do a little bit of dimensional analysis, which says that if I said 1 joule on the bottom, and on the top I put 1 kilogram times meters squared over seconds squared, I can then cancel out all of the units that I need and end up with the units that I want. And I feel like that's cheating, but again, physics says it's okay, so we're going to allow it. So now what I'm going to do is I'm going to go through and cancel out my units. In this case, cancel out 1 meter, 1 meter. I can cancel out 1 second here, 1 second here, second here, second here. Cancel out joules, cancel out joules, cancel out kilograms, cancel out kilograms. Basically, my answer is the same. Doesn't matter. But what you end up with is you end up with a value of 1.37 times 10 to the negative 10th meters. Okay, so now I'm going to convert that to nanometers. So 1 meter is 1 times 10 to the 9th nanometers, and that gives me 0.137 nanometers with the appropriate units and the math to support that. Do I think that you're going to be asked to or required to show this particular step if you're doing de Broglie's formula on an AP exam? No. But do I think that you should be aware of it? Yes. So just trying to make you aware. The homework assignment for this particular part of the notes is 6.47 and 6.48. There's a lot of work with de Broglie's formula in here, so good luck.